to differential operation. We are very good about the common mode now. We know that if you go up at the same time, the current doesn't change, ISS divided by 2. The output, differential output is 0 because ISS divided by 2 is the same on the left and right branch. We also know that there's some overdrive concept. We want to increase the overdrive, cannot do much because you may go into linear mode. We want to increase the tail current, but cannot be too much because it may go into linear mode again, right? So let's say we are good, we are at the saturation mode now. Then I want to go to the differential mode. So in the differential mode, on the left, I increase V1. On the right, I reduce V in 2, right? So this is like followed the textbook, right? The author has a very good idea in the drawing. He deliberately make the transistor higher when it means the gate bias is higher, right? Just for your visualization. It doesn't mean that there's no topological difference. And he also showed that because your left is higher, then the right will be lower, right? So you can somehow visualize this going up, this going down, causing this going down and this going up, which we discussed before already. So now let's do a qualitative sketch on the IDS1 and IDS2. On the x-axis, I put V in 1 minus V in 2. So it's not just V in 1, it's not just V in 2, it's their difference. Okay? So my question to you, when their difference is 0, what is the current IDS1? Right? This is IDS1. This is IDS2. What is the current in what are the value of IDS1 and IDS2? ISS over 2. Excellent. Yes, as long as you are in saturation, right? Everyone okay with this? Both of them. So what I'm plotting here is IDS1 and IDS2. I'm plotting both, right? They are at ISS divided by 2. I know it's difficult to see ugly, right? When I increase their difference, I increase V in 1 and reduce V in 2. How would their current? Let's look at IDS1 first. What will happen to IDS1? Increase. Do you agree? When I increase the gate voltage on the left and reduce the gate out voltage on the right, it will increase. We discussed this at the beginning of this class. It steers all the current to the left because they're more conductive, right? So it will be like this. And I claim that eventually it saturates. Do you agree? Will you just keep going up? If I keep increasing V in 1, would the current on the left go higher just forever? No. It will saturate. Why? And or saturate to which value? It starts from ISS divided by 2. This is a hint. It will go to ISS because you only have ISS. This is ideal current source, remember. It's ideal. So I don't care what happened to you. You are off, you are linear, you are saturation. I still deliver ISS. And KCL is always correct, whether you, regardless of the region you operate in, right? So this ISS, if you keep going, okay, assume you are so strong, get all my current, and the most you can get is my current ISS because I'm an ideal current source, right? So eventually, it will just saturate at ISS. And this is IDS1. Is this okay? But what if I keep reducing V in? What will happen to my current instead of increasing? It means now V in 1 is less than V in 2, so it's in the negative regime. What happened to my current? Just go down, right? Yeah. And sorry, say again, until what? Will it be negative ISS? Yeah. If it is negative ISS, it means you have current going up, but because voltage is high on top, right? So it's to 0. But when it's to 0, means it is in what operation condition? Cut off. Okay? So basically it's saying that you will go to a regime that this one is off. Then where does the current go? To IDS2, right? So if you go through the same reasoning, you will see that, you will see this one. Okay, so it's not good drawing, but you see that they all need to add up to ISS at any point. This is very important. At any point, IDS1 plus IDS2 must be equals to ISS due to KCL. That is the constitution you must obey. Okay, KCL. Okay, so good. So we have this idea. Then now look at the output voltage. So to look at the output voltage, I will do it in two ways. Right? Still, I have this x-axis as V in 1 minus V in 2. And then I want to look at Vx first. What is Vx? We know that Vx is equals to, let me start from here. Vx equals to VDD minus RD times IDS1, right? So now, when it is at ISS divided by 2, it means at zero difference, right? This one I have a typo. This is 2. I expect that I'm here. And this is VDD minus RD times ISS divided by 2. Okay? For both Vx and Vy, because they have the same value, right? Now, when the ID1 increase to the right, when V in 1 minus V in 2 is positive, what happened to the Vx? Should it increase or decrease? When IDS1 increase, should decrease, right? I expect something like this, right? And in this particular case, what is this value? This is VDD minus RDISS. Because at this moment, this branch has ISS, right? So this is VDD minus RDISS. Is that okay? And then, but if I have a negative V in 1 minus V in 2, then this will go up. And eventually, can you tell me what is the value of this point? Again, this is Vx, right? Just VDD. Why? So he is saying that when V in 1 minus V in 2 is very negative, and then the current is 0, he said this is VDD. Why? Zero current, no potential drop, right? So this is just VDD. Is this okay? Yeah. And then similarly, you go through the same reasoning because it's symmetric. I will have another curve for Vy. Okay. Again, it becomes VDD when it is V in is much larger than V in 1 much larger than V in 2. And you goes to VDD minus RDISS, right, when it is negative. Okay? But we don't care about these two curves. What do we care about? What do we care about in this definition? Differential, the difference, right? We care about the Vy, this one, V out equals to Vy minus Vx. When the differential input is 0, what is Vy minus Vx? This point. At this point, this is when the input is 0. V in 1 equal to V in 2. What is Vy minus Vx? 0. They are the same, right? So this is the output. Now if when I have very large V in 1 minus V in 2, what is Vy minus Vx? Positive or negative? Positive. And the value, I don't want to write it, but you see clearly this is equal to VDD minus VDD plus RDISS. This is the peak, right? Maybe I can write it. This is RDISS. Okay? When the V in 1 minus V in 2 is negative, what is the value of Vy minus Vx? Vy is green, Vx is purple. Is it positive or negative?
Negative RD.
Okay, so now based on this qualitative argument, I see that if I have a differential input, large signal, because it's pretty large, I can make the difference from positive to negative. And then in this region, it's pretty linear. Then you can get a linear response. If you zoom in, it's almost like a straight line. And that is the AC gain of your differential amplifier. Okay, if we only apply a very tiny difference of V in 1 minus V in 2, like 10 millivolts, 1 millivolt, this is almost a straight line. You just do a Taylor expansion, okay? But this is just a qualitative argument. I want you to understand this, right? Appreciate this. This is more important than math. Think about it. Any questions? You are there already. You say take the derivative, means that you get the slope, right? That is the small signal gain. Yeah, very good. That is the small. So I'm not going to derive it. If you really go through the equation and then take the derivative here, you find it's the same as the small signal we are going to show you later. Okay, and that is in the textbook. Good. So I know my drawing is bad, right? So I just copy the textbook. And now it's clearly showing you the Vx, Vy, but it doesn't have Vy minus Vx, but you will get the same thing. Difference of V in 1 minus V in 2. For linearity, you need to be minimal, right? Because we are doing AC signal. Yeah, we linearize the circuit. You are right, want to make it small enough. Because if you try to apply a plus minus 1 volt difference, this is no longer in the linear regime. Not linear, we cannot treat as a linearized circuit. Remember when we do the GM and R out, we only take a tiny part. Otherwise, the GM keep changing at different gate bias. Yeah, so yeah, you need to make it minimal. But however, in some application, you do need to make it large, like in RF. Then in that case, you introduce so-called distortion to your signal. And you can take that into account. You have first harmonic, second harmonic, and then you can have filter to filter all those you don't want. You just do signal processing, and you still can get something you want. Yeah, but you're right. Ideally, zero difference, almost zero difference, is the only way to make sure it is linear. Otherwise, you always have a higher order term. Okay, good question. Okay, so we're talking about the differential, right? So what is the maximum differential that I can have then, right? I already showed you this one. Now, we don't care about the saturation, right? Maximum common mode will make sure that it is under saturation. Maximum differential, it probably go into linear already, right? You think about this, maybe some already worry about when I draw this. At the beginning is saturation, but when V1 is really high, you will go to linear first, right? Here is all the linear, it won't be in saturation anymore. And then the other go to the off state, right? So in this case, we treat it as a comparator, like what you're going to do in your lab. In your lab, you will have a comparator using differential amplifier. Maybe last lab already? Yeah, you've done that already, right? This week is about the frequency response. So so here you are already in the linear regime. We just want to see what is the maximum so that it still have response, because once you go to here, it has no response already, right? So that is the so-called maximum V in minus V in 1 minus V in 2. And this is not difficult. All we need to do is just that we know that IDS1 equals to W on L mu C ox divided by 2 V GS1 minus VT squared. Now, when you reach maximum, right? When you reach maximum, I expect IDS1 equal to ISS and IDS2 equals to what? 0, right? Because you just steer everything to the left, right? You might have ISS and this is 0. We are referring to this point. Okay? So because of this, I have IDS2 equals to W on L mu C ox divided by 2 VGS2 minus VT squared equals to 0. You see that? And so it means VGS2 minus VT. But what is VGS2? VGS2 is V into minus, I call this, just call VS minus VT equal to 0. Right? VGS2, this is 0, right? So VGS2 minus VT equals 0. So VGS2, which is V into minus VS minus VT equals 0. Right? And at this moment, IDS1 equal to ISS, as we said, equals to W on L mu C ox divided by 2. Now it has VGS1, which is V in 1 minus VS minus VT squared. Is that okay? Here I'm using this equation. So V in 1 minus Vs minus Vth. Because Vg is V in 1, Vs is just Vs. They have the same Vs minus Vth, right? So I want to further change this one to V into equals to Vs minus Vt, Vs plus Vt, right? This one V into minus Vs minus Vt equals 0 means V into equal Vs plus Vt, right? So I call this equation 1. Then I substitute equation 1. What do I get? I get ISS equals to W on L mu C ox divided by 2. Then I have V in 1. Instead of minus Vs plus Vt, I have V in 1 minus V in 2. Okay? Square. Now, then you plug into the equation, you will find that the maximum I can have is square root 2 with the gate overdrive. Okay, because you just put this to the left and take square root. But you do have an extra 2 inside the square root because this is not ISS divided by 2. And then you have this. Just a concept that I want to introduce. Is this okay? Yeah. Right, so from here, you basically know that no point to apply too large comparison when you do comparator, right? If you're small, not good enough. Too large, it has no effect. Square root 2 overdrive is what you need to make the comparator to work. Okay. Now let's go to small signal. If we need to draw